Hello, this is your first video on gases. This video accompanies the notes, which you may just choose to read. I'm going to give you some notes on gases and work through the practice problems in your packet as well as some extra practice problems. Your assignment is to complete the multiple choice and the free response questions before class begins on June 3rd. We will be doing a little gas problem in class that day, and you need to be ready. So first we're going to define what a gas is. And gas, we studied this last year, is a form of matter that has no fixed volume or shape. And I think this is in your notes. Yes, it is. So there you have a further definition. A gas expands to fill the volume and shape of its container. It can be compressed, flows easily, and diffuses, which is a word that means blends. Diffuse is a word that means to blend in. It diffuses into another gas easily. So here, let's move these things around. We don't need this right now. We'll talk about that in a second. These are some examples of gases. Helium fills up balloons. Bad smells come because there are gases in the air, and the molecules in those gases are reaching your nose. This is a picture of molecules in a gas. So you can see in a gas, molecules are far apart. We're going to talk about this more in detail in 1 second. And these molecules or atoms are moving around fairly rapidly. We'll come back to this picture in a second. So here are some examples of compounds that are gases at room temperature. So let's take a look at them, see if there's any you're familiar with. Hydrogen cyanide, probably not. It's very toxic. It would kill you. Hydrogen sulfide, you may have smelled it sometimes. It smells like the odor of rotten eggs. If you've ever been near a volcano, you may have smelled this. Carbon monoxide, that's this CO, that comes out of the tailpipe of your car if you drive. It is toxic, colorless, and odorless. So when you're smelling the exhaust of your car, you're smelling other things. You're not actually smelling the carbon monoxide that will kill you. When you breathe out, carbon dioxide is another gas. You breathe out, the plants breathe it in. Methane, that when you fart, methane comes out of your butt. When cows fart, they make methane. That stinks, and that is also a gas that we can burn. Let's see, propane. If you cook on a barbecue, this is the gas that is in your barbecue grill. So you can see ammonia, you may have smelled when you're cleaning. When you clean with ammonia, that's actually a gas. That liquid solution is ammonia gas dissolved in water. These are gases that are, they are gases at room temperature. That's unlike liquids. We don't have many liquids that you're familiar with that are actual liquids at room temperature. Most of the liquids you know are things that are dissolved in water. Water is a liquid at room temperature. Mercury is a liquid at room temperature. Alcohol is usually a liquid at room temperature, but there are more things that are gases at room temperature, and we'll talk about why that is based on their structure and their polarity later on. So moving, let's make this smaller. Okay, so based on scientists' observation of gases over time, and actually the whole theory of atoms came from experiments with gases, we have developed a theory about why gases behave the way they do. So theories explain why things happen, and here we have a theory about why gases behave the way they do. First of all, and you have to memorize this. You have to know these are 5, sometimes they're divided into 6, sometimes 4, whatever. You have to know these precepts or these components of what we call kinetic molecular theory. Oops, you can't read that, can you? So the first thing is that atoms or molecules are in continuous rapid motion. And we saw that in this picture. You saw, well, this is supposed to represent here atoms being far apart and in continuous motion. So the second part of kinetic molecular theory are that the particles, the atoms or molecules, are far apart. And their volume, the actual size of the molecules, and I'm going to circle some of them here. Actually, I'll do it in pen. The size of the actual molecules or atoms is negligible, is really tiny when you compare it to all this empty space in between them. This next one is very important. We're assuming when we talk in this class about gases that there are no attractive or repulsive forces between the molecules. And we know, we just learned that attractive and repulsive forces, we call them intermolecular forces between atoms or molecules. And for this theory and the gas laws we're going to learn, we're going to assume there are no forces between the gas molecules. And then we're going to learn that in real life there actually are some. This should say the collisions between the molecules are perfectly elastic, not pretty elastic. They don't perfectly elastic, which means they don't lose any energy when they hit each other. And finally, the average kinetic energy of the particles is proportional to the temperature of the gas. So at any given temperature, all gases have the same kinetic energy. All temperature is a measure of the energy of motion of the molecules. You have these 5 things in your notes that I gave you. So we talked about how gases can be, what they are. I gave you some examples. Said they could be in balloons, or they could, or not contained, just floating around in the room. When we breathe air, we're breathing gases. There's another way of thinking about gases, and that is the word vapor. And whenever you have a liquid, so here we have a picture of a liquid, and here's the liquid, and above any liquid you do have some gas, and the word that we use for this gas that's above a liquid is usually vapor. We'll talk about this more in a little bit, but in this liquid, the molecules in this liquid, they're all moving around. Some of them will escape, and that's so you will always have a little bit of vapor or gas that is the same substance as the substance that's liquid, and it's just molecules that have escaped the liquid phase into the gas phase, and we usually call that vapor. And in fact, we're going to talk in a few slides or a few videos about the pressure of this gas above a liquid and call it vapor pressure. So we can now use the kinetic molecular theory that we just learned about to understand why a gas, and this is meant to be a picture of gas molecules, exerts pressure in a container. And the word exerts is a word that means causes. To exert is to cause, or to make happen. So before we talk about this further, let's just talk a little bit more about what pressure is. I'm going to move these over. So pressure is defined as force over area. That's what pressure is in physics and anything. It's force over area. And we're going to use an example with the ballerina to understand that a little bit better. I'll make her a little bit bigger. Bring these down. This is in Spanish. But if this lady is standing, and this is, I don't know, from Brazil, or is this Spanish? Her force, which is 530 newtons. So you can measure weight in pounds, you can measure it in newtons. So her weight is 530 newtons. And the area of her feet, I don't know if you can read this, it's a little blurry, I think is 335 centimeters squared. Area has to be in a unit of length squared. So the pressure when she's standing on her 2 feet, the pressure on her feet is her weight, the 530 newtons, divided by 335 centimeters squared, which is about 1.5 newtons centimeters squared. Now when she goes up on the tippy tops of her toes, the area that she's putting that force on is much less, and pressure is force over area. So when she's up on her tippy toes, she still has the same force. She still weighs 530 newtons, but the area of the points of her toes is much less. So the pressure on those toes is much greater. It's 14 newtons per centimeter squared, which is much bigger than it was over here when she stood on her flat feet. So this is just to illustrate that pressure is defined as force over area. So let's put the ballerina away. And we'll just, before we go to gases, talk about pressure and why. Just give another illustration. So here you see someone has fallen into the ice. Let's turn it straight. And these people are lying on the ice instead of just walking over to rescue them. Does anyone know why? You are correct if you said the pressure on the ice is less if you lie down than if you are walking standing straight up. That's because the pressure is going to be created by your weight, which is your force, how much gravity is pulling you down. And if you're just standing on 2 feet, all of your force, all of the pressure would be over this small amount of area that is your feet. When you lie down, you make the area bigger, so you make your denominator bigger here. which reduces the pressure on the ice, which is why if you ever fall into icy cold water and they have to rescue you, they will crawl on their bellies over and throw you a rope. But now we need to talk about gases, because that's why we're really here. So let's look at gas pressure. And gas pressure, remember, pressure still is force over area. That's why I have this over here. So the force is created by the molecules or the atoms moving around and hitting the sides of a container. So in this case, they're hitting the sides of a balloon from the inside. On the outside, the air, the atmosphere, is also hitting the sides of the balloon. What is the area? Well, the area is the area. It is the area that they are hitting. So here, it is the inside or the outside of the balloon. Oops. So now we'll talk about the units we use to measure pressure, and these are in your notes. A commonly used unit, which we used last year, is called the atmosphere. It's abbreviated ATM. But different units are used. 1 atmosphere equals 760 millimeters of mercury. Millimeters of mercury were used because way back when, in I think the 1700s, there was an Italian guy named Torricelli, and he took actually first we're going to talk about air pressure, and then we're going to talk about Torricelli. So let's go to the next slide. So before we talk about Torricelli, we have to just realize that air exerts pressure. And here, this is an example. If you took 1 meter by 1 meter, and you could just go up all the way up 30 miles, 40 miles into the atmosphere, all that air is weighing down on you if you were standing in that little square area, creating pressure, because all those air molecules are bouncing around in that little column, and they are essentially hitting you down way below and creating a force over this square area. So the air in the atmosphere creates pressure. So what Torricelli did was try to measure that. And so he took some mercury. He put some mercury in a tube. We'll color it silver because mercury is silver. And he put it out. And let's remember all the air molecules. Let's make them blue. They're all bouncing around up here. So air has weight, essentially. Air exerts pressure. So the pressure of the air outside the mercury pushed on it. And it pushed on it out here. And because it pushed on it out here, I need a new color. I'll use yellow. But it caused this mercury to go up. Can you see that? It's yellow. I'm going to make it green. The weight of the air caused the mercury to go up. And he measured how much it went up in the tube. And it went up 760 millimeters. That would be right there. So we said that's how we measured air pressure. Air pressure at sea level. He said, well, that's 760 millimeters, but I'm such a great guy for inventing this, I'm going to call each millimeter a torr. And that's where we got the measurement torr. But a torr is equal to 1 millimeter of mercury when you're measuring it this way. And this is still how they measure barometric pressure, air pressure, in millimeters of mercury. So now we'll think about how we use other units. So 1 atmosphere is equal to 760 millimeters of mercury. Every millimeter of mercury is equal to 1 torr, so we could also say that 760 millimeters is equal to 760 torrs. 1 atmosphere is also equal to 1.01 times 10 to the 5 pascals. And I believe a pascal, which we abbreviate PA, is the standard international unit for pressure. Sometimes, since this is such a big number, we use kilopascals, which would be 1,000 pascals, and that would be 101 kPa is the same as 1.01 times 10 to the 5th. So these are different ways that we measure pressure. You can also measure pressure if you play sports in pounds over inches. I think our air pressure is about 14 pounds per square inch. It's not just inches, it has to be inches squared. So I have to look that up. But that 14 pounds per square inch, I believe, is the same as what atmosphere? It's about that. Okay, this video is pretty long. I'm going to stop it here, and we're going to start talking about the gas laws when we come back.